Okay, let's try to learn few more different things. Okay, so sometime we have to simulate the ordinary differential equations. Okay, so how to add up the ordinary differential equation solver inside the OpenFOAM? Let's explore few of the things. So let's start with the, let's say, coding area. Okay, so let's go to the our test case. Okay, and here we going to construct the new OD solver. Okay, so let's say OD solver, ordinary differential solver, we are creating. So 002 okay, OD let's say test. Okay, so OD test, I constructed the folder. Now from where to add up this class of the solver? So first understand that. So let's go to the install area. Okay, inside the install area, okay, so couple of the things we already have. So if you look at the application and the test folder, okay, till now we always explore in the solver folder. Now let's look at the test folder. So in this, inside the test folder, you will see couple of the very nicely written few of the small code is available that will allow you to test your simple type of the subroutine, and inside of it you will see this ODE. So ODE is very simple way to define or develop our new solver to solve the ordinary differential equation. So I am adapting this ODE test from this area to our area. Okay, so and how this solver going to work? So that part is available in the SRC folder. So go to the SRC folder. Okay, and here you will see this ODE folder. So inside the ODE you will see the couple of ordinary differential solvers available. Okay, so RK Rangakutta base solver is available. Okay, then adaptive solver, Eulerian SI, ODE solvers. Okay, RKCK45, RKDP45. Okay, so many different class of the solvers is available that will facilitate the solution of any class of the ordinary differential equation. So this RK45 and that is based on the Rangakutta methods. Okay, and SIBS, this one. Okay, so it is a semi-implicit type of the solver. Okay, so then you have a trapezoidal class of the solvers. Okay, so this solver allow you to ultimately use this particular solver and give you the answer for any class of the ordinary differential equations. Okay, so how exactly this ordinary differential equation is work inside the OpenFOAM? So for that, let's explore few things, exactly how this different class of the solvers, not different class of the solver, but how this particular C code one can develop. Okay, so if you look at here, you have to add this ordinary OD solver.h file, and when you are adding this OD solver.h file, inside the file and options you must have a proper entry, so src OD included. So with the help of that, we know that whatever the solvers is needed, whatever the .h file needed, it is in line with our solver. Okay, so and here test OD.c file, and it is by default going in the user area application bin. Okay, but how this exactly the solver is built up like this way? Okay, so how to do that? So that is very nicely explained by one of the person on the internet. So let's explore this. So how to solve ODE in the OpenFOAM? Okay, so OpenFOAM is a library designed to solve ordinary differential equation. It says ODE. It is widely used for solving chemistry in the OpenFOAM. Okay, so in this post they try to explain how to exactly step by step understand this ODE solver development process. Okay, so let's explore that. So mathematically background, so we can solve any order of equation inside the OpenFOAM. Okay, so if first order, it goes straight away. If it is a higher order, then how to do? In order to solve a higher order ordinary differential equation, it should be reduced to a first order system. Okay, or first order ODEs. So basically any order equation we first reduce into the first order equations, and then we try to go ahead. So for that they give us the reference for figure as a book it is described. So, and anyway, we also know that how to change the orders of any of the ODEs. Okay, so n is the order, okay, and it is a function of anything. So n is a function of this way. In this can be reduced f y1 equal to y, then yj, okay, so yj equal to yj minus 1, okay, and finally we able to achieve the our prescribed equations. Along with that, the process could be in two step, okay, a transform of variable and differentiations, okay, here. So we first define one variables equal to y equal to y1. If let's say y2 if you want, then one is y1 equal to y, okay, and another is the y2 equal to y1, okay. So like that way we can define the process, okay. In extra step is needed in the OpenFOAM is something like this way. There is an extra step required for sufficient system solver point of view. This solver required the Jacobian matrix and the time partial derivatives, okay. So we have to construct the Jacobian matrix. So how to construct Jacobian matrix for any of the functions? So this is one, let's say f1, okay, or fn is number of equations, okay. So all is a first order equation only, okay. So all these equations we try to as many equation we try to differentiate in the all the dependent variable point of view, okay. So del f by del y1, del f by del y2 till del f by del yn, okay. So that many times we have to do that, and then along with that fn is the equation, n is the reduced order, okay. So up to what order we reduce it. Also partial derivative with respect to independent variables, okay, either it is a time or if it is xy then maybe y or x, depending on that we have to as many whatever the functions we have we have to differentiate that function with respect to the independent variables, okay. So these two things is needed. One is the Jacobian j, okay, and another is this independent differentiation with respect to independent variable, okay. So let's look at how exactly they did this, okay. So equation of motion of single degree of freedom system, simple spring mass system they explain, which is second order OD will be used as here. So m del square q by del x del y2, okay, and kq equal to 0. So this q double dot equal to minus k by m into q, okay. So m is the mass, k is the k is the stiffness, and q is the displacement, okay. The equation has an exact solution in the harmonic series, so we know the exact solution of it, okay. And q0 initial displacement, omega is the natural frequency, like this way. Now first step, transform q to y, okay. So that means we first transform this q, okay, in terms of the y. So y1 equal to q, okay, and y2 equal to q dot. So that means y1 is equal to q and y2 equal to del q by del y, okay. This equation, that means how we can transform this equation. So q dot double dot equal to minus k m y, okay. So f1 equal to we say y1, okay, first derivative equal to q1 equal to y2, we define it at y2. f2 equal to y2 dot equal to q double dot equal to minus km y, okay, km y1, okay. So that means finally what happened, we have two equations that is emerge. One equation is f1 equal to del y1 by del x, okay, del q by del y. Second is the f2 equal to this del y2, del y 1 by del, yeah, exactly, del y2 by del y, okay, and equal to q double dot, okay, equal to minus km by y1. So that is how we constructed this. Now we have a two equations, okay, and that equations we have to now differentiate with respect to y1 y2, like in case of this. So del f1 is differentiate with respect to y1 and y2. Same way del f2 is differentiate with respect to y1 and y2. So our del f1 is this one. Okay, so if you differentiate this with respect to y1, okay, because f1 equal to y2, that is what you got here, f1 equal to y2. Now differentiate f1 with respect to y1, so it is constant, so 0, and differentiate with respect to y2, it is 1. Same way here, f2 equal to minus km by y1, so differentiate with respect to y1, we will get minus k by m, and this is 0. Okay, and then with respect to the time derivatives, so f1 by dt, we don't have any time function, so this goes 0. Del f2 by dt, no any time derivative or independent variable, then it goes to 0. Okay, now how to we going to start it? So we add up the test case. Okay, we have to compile it and then we have to solve it. Okay, so that is the idea. Okay, so let's look at the implementation. So we constructed my ODE new class. Okay, and there we constructed two scalar, m1 and m2, sorry, m and k, that is nothing but the stiffness and the m both are required. Okay, and then we define this add up this mass and stiffness. Okay, this class has only three functions, namely equation, derivatives and Jacobian. Okay, so here we require the few of the things in this class. So in this class, my ODE class, we have a three functions: equations, derivatives and Jacobian. Equation represent the number of equation of the system, which essentially the order of original equation. For this is the second order equations. Okay, what it means that if you look at the existing solver, okay, so here test ODE is the class. Okay, and we define this. Inside of it we have a three part. One is the equation functions, it gives the order of the equation. So in this particular it is order of 4, so that's why it's saying the order 4. Okay, and then what else we have? Then second function is the derivative, which is the define the system of first order ODEs, like step B, whatever we constructed in the step B. So all these things we try to define, okay, inside the this particular place. So we say that del y by del x equal to 0 equal to y1. Okay, and then we say del y by del x equal to 1. Sorry, that is ultimately first equation, second equations is minus k by m, m with add slow small, okay, into y0. So exactly the same thing whatever we have at a step B. So step B, what we have, f1 equal to y2, okay, and f2 equal to k by m y1. Okay, 1 that means 0, 2 means, okay, so same thing we have, this is y1 and y0. Okay, now third final function is this class is Jacobian, and it represents the Jacobian matrix, like step numbers C. So the way we define the Jacobian matrix, del f by del y1, del f by del y2, del f2 by del f, del f2 by del y1, del f2 by del y2. So in the similar line we have to define that here. So del f by del x 0, that is first entry. Okay, del f by del x 1, okay, is also, so this is your independent variable, that is what we have here, where this del f by del x, del f by del x, f1 del f1 by del t and del f2 by del t. So here I consider the del in this case they consider dt, in case of the dt they consider the dx as an independent variable. Okay, like this is the independent variable, that is what we have. Now along with that, what we require, del f by del y 0 0, del f by del y 0 1 equal to this. Now del f by del, this is 1, del f1 by del y1, del f1 by del y2. Same way del f2 by del y, okay, equal to this. So exactly we wrote the Jacobian the way we want, and then we have a main program. So inside the main program we have to define all the properties, like what is the mass, what is the stiffness, okay, scalar functions, y0, initialization, end time, okay, and then entire of this code. So this is initialization of the velocities. So how we have to initialize initial steps, okay, then exactly the entire solution is appear inside of it, okay, and then we try to run it by this way, okay. So let's explore in the similar line couple of how this exactly whatever we are seeing here, how this particular solver is wrote for what class of the equation. First understand that, okay, so it gives us the little bit idea. So let's look at that part, okay. So let's say this is what we have here, okay. Let me close down further. So if you look at, we have a del first equations, okay, del y by del x 1 equal to 0 and 2 equal to 1. We are working with the C++ nomenclature, okay. So first ODEs, total number of ODEs, we have a ordinary equations, okay. So that is what we required is the 4, okay. So that exactly we define like this way, okay. So that is available here, okay. So we if you look at what exactly coded inside of this, so it is coded something like this way: del f, this one, del f by del f1 by del x, okay. So that is exactly the first equations what we seen here, okay. So like that way. So this is our first equation, derivatives. So in the similar line, this is the derivatives, okay. So and the number of equation in this case is the 4, in the previous case it is 2, okay. So it is a fourth order maybe ODEs, and we reduce to the 4 one order ODEs, okay. So that is what, so this del y1 by del x1 is nothing but del y by del x0 1 equal to 0 equal to minus y1. Then second is del y by del x1 equal to y0 minus 1 by x into y1. Third one, del y by del x2 equal to y1 minus 2 by x into y2, okay. Same way, del y by del x3, this is equal to y2 minus 3 by x y3, okay. So that is all the ODEs. Now we have 4 ODEs, okay. So that means if you come back here, so look at the Jacobi. So Jacobi, if you look at here, so we have f1 by and total 4 ODEs. So we require the del f1 by del y1, del f1 by del y2, del f1 by del y3, and del f1 by del y4, okay. So in the similar line, if you look at now, just look at the Jacobian, okay. So we can calculate the Jacobian for x and y, okay. So first is we have a del f okay. So let's so first we have a del f1, okay, by here, okay. So this is what del f1, okay. I think the first one is the independent variables. So let's come back here. As many equations we have to differentiate with respect to del x, okay. So that is what we have. So first equations, okay. So we have a del y2 by del x equal to 0. Second one here, this one, okay. So del of y1 minus y2 by x equal to this. So we will get y2 by x square, okay. Then here we will get something like 2y3 by x square, and here we get 3y4 by x2, okay. So this is all the independent variables. Now look at the ODEs. So first one we have to differentiate with respect to y1, then y2, y3 and y4. So if we differentiate with respect to y1, we get 0 because here only y2 minus 1 all are zeros. This also we have to differentiate with respect to y1. So if we differentiate y1 1, y2 1 by x, like that way we constructed all the Jacobian here. So in all the Jacobian we supposed to write it down here. So this is all independent part of the Jacobian, that is this del f1 by del x, del f2 by del x, del f3 by del x, del f4 by del x. Okay, so that is exactly this del f by del x 0 1 2 3 4, and this is about all these entries. Okay, then del f 1 by del y1, so 0 0. Okay, del f1 by del y1 equal to 0. Then del f1 by del y2, del f1 by del y2 equal to minus 1, del f1 by del y2 equal to 0, del f1 by del y4 equal to 0. Similar line, del f2 by del y1, that is this one 1, then del f2 by del y2, this one. In the similar line we write all the Jacobian. Okay, so what we needed, number of the equations, then derivatives, exactly how our equation look like. Okay, then independent variable differentiation and the Jacobian. So with the help of that we are set with all the solver part whatever needed for this. Okay, along with that in the main code we have a few more entries like initializations. Okay, how to initialize and then how to solve it. Okay, so before we develop our new ODs, let's try to compile it and solve it and have an idea how exactly it's working. So let's go to the OD area. Okay, wmac. Okay, so we are set with this. Okay, now if we want to run it, few things required. We have to define the solvers. So let's say you don't know what type of different solver available, then write down, let's say test. So if you write, it will show you all this available solver, and that all the available solver entry you will see inside of this src folder. So it give you the idea that many class of the solvers you can run with this. So how to run our executable name, let's say we want to work with this rkcd45. Okay, so this is how it's give you the final answer, analytical solution. Okay, and numerical solutions. Okay, so that is exactly one can simulate step by step. Okay, so that is how, and real tolerance, how the tolerance is reducing. Okay, so all the entry is like this way. So let's now develop a new entirely one of the solver. Let's say we want to solve this new ordinary differential equation. So how to go about it as a new solver development? So let's develop this particular ODs. So what we supposed to do in the similar line what we look at here. Okay, so we first have to define a new class myOD. Okay, and we give the new name as a some different OD name. Okay, so let's go here. In case of this let it be OD test only. Okay, but we try to change, let's say class name, we say it's my OD. Okay, that is the name we define. Okay, and under the my OD name, okay, we have a now number of equations. So let's look at the order. Our order of equation is second order, so definitely it's supposed to be the 2 only. Okay, because we reduce the order, so we need not to go for a higher order. Now what is the next task? If you look at our ordinary differential equations, it is del square y by del x2. So independent variable is the x. Okay, and then we have a equal to y, and we have a condition y0 equal to 0 and del first derivative of y equal to 1. Now change our OD to the first order OD. So we define del y by del x equal to z. okay. And then we say that del z by del x equal to y, that means y equal to 0, and this equal del z equal z0 equal to 1, okay. So Jacobi for x, that means independent variable. Now if you look at, this is the f1, okay. So del f1 by del x equal to 0, del f1 by, del f2 by, this is function 1, so f1 is nothing but z, f2 is nothing but y. So we, to construct the Jacobi and all this part, what is needed, we have to create the derivative with respect to independent variables. So here independent variable is the x, okay. So what we are doing, we say that del f1 by del x is equal to 0, del f2 by del x equal to 0. Why? Because f1 equal to z and f2 equal to y, okay. Now we construct the Jacobi. So what we required, del f1 by del y1, del f1 by del y1, okay. So del f1 by del y1, okay, so that is equal to 0, okay. Then del f1 by del y2, so it is exactly 1. Then del second part, we required the del f2 by del y1, okay, del f2 by del y1, okay. And then we required the del f2 by del y2, okay, that is equal to 0. So now we supposed to modify in the similar line our code, okay. So to incorporate all the entries inside the solver, we have to modify our solver, okay. So let's do that here. So first, this is our derivatives area. So inside the derivative area, so first let's define our these things, okay. So let me, yeah, so let's look at here, okay. So my OD system, okay, OD system is same. I cannot change the OD system. I supposed to change only the class name, okay. Let it be OD system, and this is OD test, okay. Let it be right now OD test. Later on we replace with the OD test, or let's replace it my ODE. Entire document, wherever we have, everywhere we change to my ODE, okay. So at a time, fine. Now let's construct the solver. So what we needed the number of equations. So number of equation is 2, okay, 1 and 2. Now we supposed to write the equations here, okay. So number of equation is 2. So first equation is what, del f1 by this one, okay, del f1 by del x equal to y1, okay. And second equations is del y by del x equal del y1 by del x equal to 0, okay. So that is what we have, number of the equations. So let's write down that, okay, this number of equations from here to this area. So we have a del y by del x, okay. So del y by del x, okay, equal to del y by del x equal to, we have a this one, and z, please remember z is nothing but the y1, okay. So we replace this z equal to y1 only. So and in our case this is positive, okay. So that is what we have. Then second, we have a del y by del x 1 equal to y of 0, because that is the second part, okay. So this is we don't have anything, so it is goes as a 0, so we don't have any entry here. So let's, it is how one can write it down. So look, del y by del x equal to y1, okay, and then del y by del x of 1, okay, is equal to y0, okay, fine. Now let's look at the Jacobian, Okay, so for Jacobian, first we write for the independent variables. So that is the independent part is this one. Okay, so let's both is 0 0 only. So sorry, let's first delete this. So del f1 by del x equal to 0, then del f2 by del x equal to also 0. Okay, so that is the independent part. Then we have to fix this Jacobian in it. Okay, so Jacobian we require only 4. One is for 1 and another for 2. So one for 1, another for 2, rest are not required. Okay, so that many things only goes. So del f by del y 0 0 equal to 0. Okay, del f by del y equal to 0. Then del f by del y 0 1 equal to 1. Okay, so that is become 1. Then del f 2 by del y equal to 1. 2 by del y equal to 1. Okay, then del f 2 by y2 equal to 0. So that goes as a 0.0. Okay, so we are set with this all entries. Okay, now let's few change whatever needed. Let's look at. Okay, so initializations, we required initializations for both the things. So y start and this thing equal to, so y start for 0 equal to 0 and y start 1 equal to 1. So let's look at here. Okay, so scalar start, let's say initializations, let's start with very low value. Okay, then scalar y start. Okay, so scalar y start x start, then scalar y start 1 equations, fine, but here I will explicitly mention the values whatever we needed. We needed equal to y1 equal to 0 and y2 equal to 1. Okay, so that is exactly we supposed to write y0 equal to 0. Okay, that is what, that is nothing but y of 0 equal to 0. Okay, so that is nothing but this entry. Okay, and this is equal to 1. Okay, 1.0. so what it mean? It mean that y dash 0 equal to 1. That's it, that is available here. Okay, so that is what we adapted. This is not required. Okay, so I think that's it. Let's solve it, compile it and solve it. Okay, so let's compile and solve it. Okay, okay, so we are getting this memory corruption error. Okay, corrupt. So it is because of few of the things that is missing inside the solver. So let's explore. So up to here it's fine, we modified it. So this is how to initiate the derivatives, fine. So this is enter calculations, that is also fine. Okay, here is the problem because we have now only 2 equations, so it's going till the 4th one. Okay, so then analytical result also not required, so let's delete that. Okay, and this is numerical, not y equal to, so numerical result we supposed to have a answer for that. Okay, so let's try to compile it again and run it. So that's fine. So we are we have a answer of 1.175. okay, and this is y equal to 2 definitely because number of equation is 2. So that is how one can quickly create this this ordinary differential solver and run it very quickly. Okay, so how we proceed, we follow this very nice link that is online available and try to understand exactly what is the Jacobian, okay, and how to construct all the entries. So that nicely explained here, okay, with the help of the spring and mass balance class of case. Okay, and then we try to run it with the help of the RKCK45 solver. Okay, so that is what we did. Okay, so if you want, they also have some analytical solutions, okay, here, so you can implement this and try to compare both the answer as well. Okay, so and then you can also, because the analytical solution is available, okay, so you can apply that solutions and check how exactly it's look like. Okay, motion equations. So that is how one can very quickly develop the one ordinary differential equation based solver inside the OpenFOAM.